Today we are going to be taking a look at some of the graphs of some classic polar functions, specifically circles and what are called roses. So there are several classic polar functions. They are the circles, roses, cardioids, and limacons. And you need to recognize their equations and know how to graph them. Okay, so circles, we all know what circles are. Okay, the ones that we are going to be looking at are the ones centered at the origin and the ones centered on one of the axes. Okay, notice that all the ones that we're going to be looking at, they are on the origin, so they go through the origin, each one, and they are on an axis. We're not going to be doing the ones that are off of the axis at all. Well, we can think about them, but we're not responsible for knowing how to graph those kinds. And then the roses. So the roses look a little bit more like daisies than roses, but they are called roses. Okay, we're going to be looking at those two today. And then next time I see you, we're going to be looking at cardioids and limacons. Okay, first of all, circles. The circles have two types of equations. The first type is just r is equal to a number. Okay, when you have r is equal to a number, that is a circle centered at the origin with radius whatever the absolute value of that number is. The other two types, or the other type, is r is equal to a cosine theta or r is equal to a sine theta. If it's a cosine, it sits on the x-axis. If it's a sine, it sits on the y-axis. The a gives you the diameter, not the radius, the diameter. Okay? And it's always the absolute value of it. If it's positive or negative, that will tell us where it goes. Alrighty? Okay, let's begin with centered at the origin. So centered at the origin, these circles have equation r is equal to some number, like r is equal to 2 or r is equal to -1. So these will all be centered at, think of it this way, if we were to make a theta r little, if we were to plot some values, when theta is 0, r is 2. When theta is pi over 3, r is 2. When theta is pi over 2, r is 2. So if we plotted all those, when theta is 0, r is 2. When theta is pi over 6, r is 2. When theta is pi over 4, r is 2. R is 2, r is 2, r is 2, r is 2. R is always 2, no matter what theta is, r is 2. So that gives us the circle of radius 2. Okay? R is equal to -1. So when theta is 0, if we do the same thing, when theta is 0, r is -1. So that point would be when theta is 0, r is -1. When theta is pi over 6, when theta is pi over 6, r is -1. When theta is pi over 4, r is -1, etc. So this circle would be like that. And the finished product is the same as the graph of r is equal to 1. Okay, the finished product is the same, but to get there, it's different. This would start here. If r is equal to 1 would start here and go around like that. This one would start here and go this way. Okay? Alrighty. Now let's go off the axis. I'm sorry, off the origin. So a circle on one of the axes. So if you have r is equal to 3 cosine theta, r is equal to 3 cosine theta, that, here's what I want you to think. It's a cosine, so I want you to think x-axis. If it's a sine, you think y-axis. This is a positive cosine, so think positive x-axis. positive x-axis, diameter 3. Positive x-axis, diameter 3. Negative x-axis, diameter 4. Negative x-axis, diameter 4. Positive y-axis, so positive y-axis for sine, diameter 3. Okay, and negative y-axis, diameter 2. That's how we graph those. Okay, one more thing. For a circle centered at the origin, like these, we need to go from 0 to 2 pi to get one complete graph. For these circles off the origin, we need 0 to pi. We only need 0 to pi for one full graph. Okay. Alrighty. So that takes care of the circles. Now let's talk about the roses. Alright. So roses, what's different about the equation for a rose? Well, for if in here you have a number in front of your theta, a number other than 1, a number other than 1 in front of your theta. If that's the case, you no longer have a circle, you have one of those daisy looking things that we call roses. Okay? To know how many petals your daisy or your rose is going to have, the rose will have n petals if n is odd. And if that's the case, you need 0 to pi for one full graph. If n is even, you have double that number petals, and you need double the length to get one full graph, 0 to 2 pi. So odd, even, for this theta coefficient. All right, for the cosine roses. Cosine roses, if n is even, and you have cosine, then you're going to have petals on every axis. So when I think of cosine, I think I know I'm going to involve the x-axis. I know I will. Okay? So cosine with even petals like this one. So I think to myself, 2 theta, so 4 petals. Each petal is going to be of length 3. Okay, the next thing I look at is the sign here. It's a positive cosine. So I think to myself, positive x-axis. Positive x-axis, 4 petals, each of length 3. Okay, now I'm going to show you something when we graph this. You guys, when theta is 0, here, when theta is 0, I'm going to have cosine of 0, right? Cosine of 0 is 1. 1 times 3 is 3. So when theta is 0, I am out here at 3. As theta goes, as theta increases, I'm going to be forming my first petal, and it's going to go like this. And then it's going to keep on going around like this, and like this, and keep going around, and then we're approaching 2 pi for theta, and it goes like that. Okay? Notice that it does not, I don't want you to think of this as going like this. Okay? That's not how these form. This is a very smooth curve. Think of that on the XY graph. Very smooth curve, right? Very smooth. So there's no bouncy bounces. It doesn't go boink, 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 boink. There's no boinking. It's smooth, all right? So when it starts out, it goes like this. Don't stop. When you get to the origin, don't stop. Keep on going. Keep on going nice and smooth. Trust me, if you do this, your roses may not look the best, but I promise you it will help you analyze them. We're going to be doing more with this. So I'm not interested in just what is the finished product. I'm interested in how it's formed. So it keeps on going around really nice and smoothly like that. Okay? So avoid the bouncy bounces. Okay? Alright. So if this is a negative, if this is everything is the same except it's a negative. For even, it's not going to change the final product. It only changes how it's formed. This time when theta is 0, I'll have cosine of 0, which is 1, times a negative 3. When cosine is 0, we're over here at negative 3. And as theta goes up here, I'm going to be negative, so I'm going to be down here. So as theta is going around negative, around from 0 and increasing, my R value is going to be negative, so it's going to put me down here in the third quadrant. So this is going to go like this when we start off. So it's going to go like that, and then nice and smooth, around and around, nice and smooth like that. Finished product. Finished product is identical. They both have petals of length 3. Both of them do. But they were formed in very different ways. Okay, this one. This one is going to have 8 petals. 8 petals. And it's a cosine, and it's a positive cosine. I know I'm starting on the positive x-axis right there. Okay? 8 petals. Okay, 8 petals are harder to draw than 4 petals are. Okay? 8 are harder to draw. I will tell you that. Think about where we're going. 1 petal is here. The other 7 are evenly distributed around. Right? Just like these petals were evenly distributed. Right? Evenly distributed. So I know I'm going to have petals on each of these axes. And I'm going to have petals halfway in between at the 45 degree angle, at the 45 degrees, pi over 4 angles. Okay? So when we're starting this positive, I know when theta is 0, I'm starting out here at 5. Think about where it would go. Where would it logically go to make a smooth curve? Well, I'm thinking it would go like this. The petals are going to be thinner. But to be nice and smooth, it's going to go something like this. Oops, I got really goofy on that one. Okay, do you see where I overlapped? It shouldn't be overlapping, okay? When you graph for me, that's not going to bother me that much, but do your best not to make them overlap, okay? They should not, they never overlap. These are non-overlapping petals, okay? Now, I'm looking at my finished product, and it does not look all that even. Some of the petals look way fatter than other petals, right? I'm not going to be grading you on your artistic abilities, okay? But it is important to me that you know how many petals, where the petals are, and that they are smooth, okay? They are smooth. They are not bouncing. You don't bounce to get to each petal, okay? It is smooth, okay? This one's going to be even tougher because this has how many petals? 12 petals. It's a cosine, and it's a positive cosine, so again, I know I'm starting on the positive x-axis because when theta is 0, cosine of 0 is 1, and 1 times 4 is 4, so I know I'm starting there. And as theta starts to increase, my r is going to be positive because I know what the cosine graph looks like. Okay? And cosine always starts positive. Alrighty? So, I need to distribute the other 11. I know there's going to be a petal here. It's going to be thin. I need to distribute the other 11 petals around. So I know I'm going to have them on each of the other axes because it has to be distributed. And then I need to put 2 in each of these quadrants, right? I need to put 2 in each of them. So, and it needs to be even, so just do your best to make them evenly distributed, okay? It helps me to put these like little dots where I know the tips of my petals will be. Okay? So where would this first petal, after it leaves this first petal, where would it go to? I'm really not sure where it's going to go to. I might, I don't know if it's going to go over here. I'm kind of going with it, but I'm really not sure if this is right or not. I think it's going to work out fine. Okay, it did work out. This time it worked out. I will tell you that I've done this before and I just don't choose the right path. But there are 12 petals. 12 finished petals, each one is of length 4. This one was of length 5. This one was of length 3. Okay? Alright, this is a great time for me to show you, and I did not bring home my good graphing calculator, but this is a good time for me to show you what our calculators can do. Okay? We are always in function mode, but there is a polar mode right there. So I'm going to go down to polar mode. And now when you hit y equals, it's not going to be y equals, it's going to be r equals. R1, R2, R3. Instead of y1, y2, y3, R1, R1, R, etc. Okay? I think I might go ahead and graph this one. Okay? But so that it all shows up on my graph, I'm not going to make it of each petal of length 4. I'm going to make each petal of length 3. That way I can do it in a nice 1-to-1 ratio. Okay, cosine of 6. And when I hit this x, it's no longer going to be x. It's going to be theta because we're in polar mode. Okay, interesting, huh? And now I'm going to go to my window. I'm going to go to my window. So the last time I was in polar mode, I clearly was going from 0 to 2 pi, because 6.28 blah 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 is 2 pi. Look at the theta step. I like that is default. I like to slow that down. 0.13 is going to go really fast, and I don't want to go that fast. I want to go maybe 0.05. Okay, my x-min and my x-max, -1 to 2, and look at my y-min over here. I don't want that, but I'm going to fix that with zoom 4. Once I go to zoom 4, I think it'll do it automatically. So zoom 4, and here we go. There's the graph. Great. I think we did pretty good. Now, doesn't it look kind of choppy? Doesn't it look kind of choppy? And even that, you saw how quickly it went, right? If you make this smaller, if you make that smaller, it will take longer and it will be more accurate. That zoom 4, by the way, it made my graph be each y unit was the same distance as each x unit. That's what that zoom 4 does, by the way. Okay, let's do it again. You see now it's going more slowly and it's a little less choppy. Still kind of choppy. My other calculator is a little bit better. But I like this because I can really see how it's graphing, not just the finished product, but actually how it's being formed. And you can see that you need 0 to 2 pi to make one complete graph. Now, another thing I like to do is I like to go over here, right there, and if you hit enter, and hit enter, right now if I left it like that, it would just make it a thicker line, a thicker point. This is the one I like. I like this one, this bouncy circle, okay? When I do that, you can see where it's at, and you can see if it started to go over itself, you would notice that. I'm not going to watch this all graph again. If you ever want to stop a graph, you do second on, and it just stops your graph from graphing. Okay, you never have to sit there and wait for it to finish. All right. Okay, enough of the calculator. Let's get back here. If n is odd, and you have a cosine, then you must have one petal on the x-axis. Make that petal. Show where that petal is going to be. Positive x-axis if you have a positive cosine, negative x-axis if you have a negative cosine. And then draw your petals evenly around. So, 3 cosine 3 theta. 3 theta, so 3 petals. Each petal is of length 3. Lots of 3's going on. Okay? Positive cosine, positive x-axis. The 2 remaining petals are evenly distributed. So evenly distributed would put a petal like around here and around here. And once again, to get there, no bouncy bouncies. We're going to go like this. Oops. That. And like that. Let me come back to my graph. I'm going to go back to my y equals 3 cosine 3 theta. Let's graph that. Kind of slow. I'm thinking about going back to the 0.05 because that's pretty slow. It's pretty darn slow. Okay. I'll change that for our next one if I get back on here. Alright, look at it. There it goes, just as expected. There it goes. We're still going. That 0.01 theta value, it is plotting a point every 0.01 theta. That's really a lot. We're about to finish. Are we going to finish? Oh. What's it doing? Why is it going back over the graph? Why is it going back over the graph? It's going back over the graph because it's going from 0 to 2 pi. So it's going back over itself. For even petals, you need 0 to 2 pi. For odd petals, you only need 0 to pi to get one complete graph. If you go more than that, you're going to be going over your graph again. Okay? Alrighty. Alright. A negative will not change the, the negative with odd petals. Negative with odd petals. So odd petals, 5, so 5 petals, cosine and a negative. So the first petal, here's what my thought is. The first petal is going to be on the negative x-axis. Think of it. If you put 0 in for theta, you'd have 1 times negative 3. You'd be back over here. Okay, by the way, each petal length 3 on that one. All right, this is going to be 5. All right? Okay, 5 petals distributed evenly around. So it's going to think about a star-shaped, like a nice starfish. So maybe like here and here and here and here. Nice star shaped. And when we start, think of theta is increasing, but r is negative, so it's going to display down here in the third quadrant. So it's going to go like that. The more petals you have, the thinner the petals are. I like that. It's so fun. Okay? All right. 3 petals, negative cosine. So there's a petal on the negative x-axis, and it has length 5. But there's only 3 petals. So evenly distributed, it's going to go like this. Like that. Something like that. I made my petals way too close to the y-axis here. It should have been much further out, but whatever. I am not grading on that aspect, okay? So just do your best to get those around there. Try to make them look like they're evenly distributed around there. I did a better job on this one, didn't I? That one looks better, more proportioned than this one. Okay, 7 petals. Positive cosine, so there's 1 on the positive x-axis. 7 petals. 7 petals, that's a hard one to do, and hard one to do right. But I'm going to have 5 petals, I'm going to have 6 petals around here, right? So I'm going to like try and do my best. All we can do is our best, right? Does that look evenly distributed? No, it doesn't. Whatever, okay? Just do your best on that. And I don't know how this is going to work. I don't think this, see, I messed up. So just to make it work on the end, I'm going to finish it up like that. That's usually how it happens. My finished product looks good though. I like my finished product. I just am not sure how to get there. What did I do? I think I needed to go over this way. I think I went down here, and I think I needed to go out there. Okay. Anyway, there's your finished product. Positive cosine, positive x-axis every time. Let's write the equation of each of these graphs. Okay. I see a petal on the positive, it's 3 petals and the positive x-axis. So this is going to be r is equal to positive, the length is 3. It definitely is a cosine, and there are 3 petals, so 3 theta. There are 4 petals. Each is of length 4, and I notice that there is one on the positive x-axis. So I'm going to make this r is equal to positive 4 cosine 2 theta because it's 4 petals. This, by the way, we could have said was negative 4 cosine 2 theta because of this negative x-axis also. Either one. Both of these equations produce this as a final graph. But you cannot do that on the odd petals. Okay. Odd petals, negative x-axis. So this is going to have to be a negative 3 cosine, how many petals? 7. Okay. Positive x-axis and negative x-axis. So this is one of those that could be positive or negative cosine. R is equal to, I'm going to make it a positive. What is this? 1, 2, 3, 4. 4 cosine. Okay, how many petals are there? I know it's even. Okay, 1, 2, 3, 4 times 4. So there are 16 petals. So this has to be an 8 theta. And R could be negative as well. Okay, let's take a look at how we do it on time. 30 minutes. This is a long one, huh? Okay, let's take a look at sine roses. If n is even and you have a sine, then you're not going to have petals on any x-axis. All petals lie in between the axes. Okay? Once again, just like for cosine, if a is less than 0, it does not change the shape of the final graph. So here, when I see sine of a 2 theta, well, it's 2 theta, so I think double the petals. So 4 petals. It's a sine. If it was a cosine, we'd have petals on every axis. But it's a sine, so we have petals on no axis. Okay? When theta is 0, sine of 0 is 0, so we're starting right at 0. Okay? That's the difference. When theta is 0, you're 0. So we're going to have a petal at pi over 4, at 3 pi over 4, 5 pi over 4, and 7 pi over 4. When theta starts to grow, we're going to be going like this. R gets positive, right? Because sine goes up, right? So we're going to go out to 3, and then around like this. Are we going to bounce when we get to the end? So we've gone like this. Are we going to bounce? No, we're going to be nice and smooth and go through. Whoops. Like that. Nice and smooth, go through. Nice and smooth. And finish up. And when we finish up, we are at theta equals 2 pi. It takes 2 pi to get there all the way around. Okay? If there's a negative, your final product is the same. But to get there, it'd be different. Instead of going around this way, we're going to be going around this way. Okay? So, but the final product is going to be the same. So it's going to go like this. Oops. Oh, I was doing so good. Okay, well, I failed at the end. Oh well. Oh well. Result is the same, but getting there was different. Okay, 4 theta, 8 petals. It's a sine, so no axis. No axis. 8 petals. So I'm going to have 2 in each quadrant. So 2 in each quadrant. Just kind of space them out. We want them to be spaced evenly, right? Okay. As we start, it's going to go like this. I try to do this the way it would probably land. Very daisy-like, okay? It's worthwhile to show this to you on my calculator. Take a second to do that, but well, I'm going to change this to a sine. Let's just do one of these. Let's just do 3 sine of 2 theta. And I am going to make this 0.05 so that it goes a little bit faster. And it is going 0 to 2 pi still. So we see exactly how it's graphed as theta goes from 0 to 2 pi. We have some negative r values in there, so that's going to make it. So the end, you don't see it hitting the origin, but it actually does hit the origin, but here you can't see it, right? Okay, looks rather butterfly-ish on that. Okay, 6 theta, so 12 petals. So let's see, that means 3 in each quadrant. So 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. something like that. This is going to be rough for me to do, but it's going to go out like that. I don't know. I don't know where this is going to go, you guys. Maybe like that. No, I know it's not going to do that. Okay, so to finish this up, I'm just going to fudge it. I know I'm going to need a petal here, and I know I need a petal there. Okay, just make it work, you guys. When you get a bunch of petals in there, it's hard to make that work, but in the end, make it work. Okay. If n is odd and you have sine, then you do have one petal on the y-axis. But the placement of that one petal gets tricky. It does not, notice, each of these is positive. But do you have a petal on the positive y-axis? No, not every time. Okay, it gets tricky. So you are not going to be responsible for graphing these. Okay, you're not going to be responsible for graphing a sine with odd petals. Okay, but you need to know that if it is a sine with odd petals, that you are going to have one petal on the y-axis. Alrighty? You just don't need to know where it is, positive or negative. Okay? I will say, this is when the theta coefficient is 1. This is when the theta coefficient is 3. So when the theta coefficient is 1, when you have one petal, you have a petal on the positive y-axis. 3 petals, negative y-axis. 5 petals, positive y-axis. 7 petals, negative y-axis. 9 petals, positive y-axis. 11 petals, negative y-axis. 13 petals, positive y-axis. It alternates back and forth like that. FYI. So I could require it of you, but you just don't need to know that. Alrighty? So this is how you might be asked a question. Which equation could be the graph of this, could make this graph? Which equation could make this graph? Well, I see a petal on the y-axis and it's not on the x-axis. Since it's on the y-axis and not the x-axis, I know this cannot be cosine. Cosine is always on the x-axis. So it has to be a sine. This sine has 3 petals, this sine has 5 petals, so it must be D. Because this does not have 3 petals, it has 5. Okay, what about this one? Okay, y-axis, not an x-axis, so not cosine. How many petals? 3. Okay? X-axis must be cosine. Must be cosine, not sine. How many petals? 3. Okay. All right, for this one. Y-axis, but not x-axis. So cannot be cosine, must be sine, and it has way more than 3 petals, so this must be D. So that would be a typical test question for seeing, do you know what the graph of an odd petaled rose with a sine equation looks like? Okay. One more thing before we end for today. Oops. Talking more about how the graph is formed. Okay, let's consider this graph and let's show how it is formed starting with theta is equal to 0. I'm going to make a little theta r chart. When theta is 0, what is r? Well, cosine of 0 is 1, and we'll have 4 times 1, which is 4. When theta is 0, r is 4. 1, 2, 3, 4. Okay? I should get a different color going on here, something more bright for this video. Okay. When theta is pi over, I don't want to do pi over 6 because that won't get me a nice number, but I will do pi over 3. We'll have 4 times 1/2, which is 2. When theta is pi over 3, we're at 2. Okay? Oh, that's not 2. Hang on. 2 would be, think of 2 as like 2 is on this circle here. So at pi over 3, 2 would be like right there. Okay? When theta is pi over 2, when theta is pi over 2, we have 4 times 0, which is 0. So at pi over 2, we're at 0. And I know what the final graph looks like. It goes like this. So it goes this way. And it finishes at pi. At pi, we're back to 4. Let's answer these questions. On the interval from 0 to pi over 2, from 0 to pi over 2, is r, when you see f of theta, think that's my r. Is r positive or negative? Well, r was positive there. Okay? On that same interval, is f, which is r, is f increasing or decreasing? Was r increasing or decreasing? Well, we started at 4 and we ended at 0. That means it was decreasing. Okay, on the interval 0 to pi over 2, is the distance between a point on the curve and the origin increasing or decreasing? Is the curve getting farther from the origin or closer to it? Think about that. Are we getting closer to the origin or farther from the origin? Well, clearly we're getting closer to the origin. We're getting closer. So the distance is decreasing. You're going to be asked questions like this, okay? Next up, from pi over 2 to pi, is r positive or negative? Well, you guys, oh, I should have said that r, up here, when theta is pi, r is negative 4, not positive 4. If it was positive 4, it would be out here, and it's not. It's over here, all right? When we are after pi over 2, r has to be negative because we have nothing showing in this quadrant. It's all showing down here. So r must be negative. R must be negative from pi over 2 to pi. Negative. Okay? All right. Is r increasing or decreasing? You guys, what is f of pi over 2? What is f of pi over 2? That would be 4 times cosine of pi over 2. Cosine of pi over 2 was 0. So that would be 0. What is f of pi? F of pi is 4 cosine of pi. Cosine of pi is negative 1. So that's negative 4. We're going from 0 to negative 4. So are we increasing or is r increasing or decreasing? It has to be decreasing. Has to be. To go from 0 to negative 4, we got to be decreasing. Is the distance increasing or decreasing? As we go from this point to this point, is the distance increasing or decreasing? The distance from the origin to the point on the curve, is it increasing or decreasing? It is increasing. The curve is getting farther away from the origin. Okay, this was kind of a long one, but I needed to spend a moment talking about that increasing and decreasing stuff. So that is it for polar circles and polar roses, with a discussion on increasing and decreasing.